Hey everyone, welcome to the last video for section 2.9. So in this video, we're going to see what happens when you push beyond rho equals 3 for the logistic difference equation. So we know that 0 is stable for rho less than 1, the other equilibrium point is stable for rho between 1 and 3, but what happens if you go beyond 3? That's what we're going to talk about in this video, and things get pretty crazy pretty quick if you go beyond 3. Let's go ahead and jump on into that. So the big question for this video is, what happens for rho bigger than 3? So the answer is it gets crazy. So for rho bigger than 3, we see a period 2 orbit develop. Now what I mean by this is there are two values that whatever initial condition you start with, the solution will converge to oscillating back and forth between those two values. So it's like there's like a 0.57 number and a 0.7 something number. They're in the book. You can look at them there. But the solution just starts oscillating back between those two numbers. It doesn't converge to the one equilibrium point. It splits away from that, and there are two values, one on either side. It just keeps bouncing back and forth, back and forth, back and forth between those 2 points. If we're anywhere between 3 and about 3.449, this happens. So as long as we're not, rho isn't too big, if rho is between 3 and 3.499, give or take, then any initial condition I start with, it will eventually converge to that period 2 orbit, bouncing back and forth between those two values. So let's take a look at that in the maple stuff that I've written up and see what happens there. So here I wrote some code to do the sort of processing we were talking about before. So I pick an R value, I can solve the equation, R is my rho in this case, and see what happens. So let's say I set R to be 3.1. My notification is 0.3. So let me run the code, and that's what I get. I get the box there between those two values, and if I plot the solution, I get something that oscillates after a finite number of steps. I can go in and change my initial condition, and say I change it to 0.7. Same thing happens. I get the same two values and the same oscillation. So it doesn't matter what I pick, I will get the same oscillation going on between these two values. Now, what things start getting crazy as rho gets bigger, I see higher periods develop. So as rho increases, I'll see period 4 orbits, I'll see period 8 orbits, I'll see period 16 orbits. And if you look at the critical values, so the first value of rho where those things emerge, what you end up seeing is that these rho values end up converging to something. So they're not going to go off to infinity. So the rho values where the first new period emerges converge. They converge to something around 3.57. So another term that I want to define here is the idea of a bifurcation. So each time these new solutions develop, these new things appear, that's called a bifurcation. A bifurcation means when you change the parameter, this rho, you get new types of solutions that form. You'll see some of those in one of the projects that I'm giving you. But the idea is that as you change rho, new solutions emerge. So with for rho less than 3, there were no period 2 orbits. Everything converged to something. But at rho equals 3, you get a period 2 orbit developing. At rho equals 3.5-ish, 3.45-ish, you get a period 4 orbit developing. So these are all called bifurcations. All right, so all these rho values converge to 3.57. So what happens beyond 3.57? Theoretically, we've gotten to period whose orbits are of order infinity, basically, because you get these converge to 3.57, you can get as many as you want before then. So what happens beyond that point? What happens beyond there is what's called a chaotic solution. So why these solutions are called chaotic is because they oscillate, but they don't oscillate in a predictable manner. They're kind of random in where they go up and down and how they move around. They're really kind of random in what they do, so chaos, random things. And also, they're extremely sensitive to initial conditions. So these guys oscillate kind of randomly, and are very sensitive to initial conditions. All right, so let's take a look at some graphs of those in the maple stuff and see what we get from there. So now I want to go back up here and I want to make my R value say 3.8. Run the code. It doesn't draw anything on the graph, and it doesn't do that because it doesn't find a periodic solution. That's kind of the point of what it's doing. So if I try to draw it, what am I going to see? Chaotic stuff. The idea is it's oscillating up and down, but it's kind of really random in how it does it. It's not really predictable into how it's doing everything and where it's going. It just kind of jumps up and down at random times. And now this is my initial condition for being 0.7. So I'm going to save that for a second. And now I'm going to change my condition to 7.0001. So I'm off by a very, very, very tiny amount compared to what my condition was. Let's run this code, draw the graph, and now what I want to do is I want to draw those two graphs side by side. So the red is going to be the first one we drew, this is 0.7, and the blue is going to be 7.00001. Ready? They're not the same. They're in fact very different once I get about 20 steps or 30 steps out of my equation. So they're pretty identical for about the first, 20, 30 steps or so. But by the time you get about step 30 or 40, they're not even connected at all. They're very different. They're scattered, doing whatever they want. They're not even close to the same equation out here. And this was me changing the initial condition by 1/10,000th of a number. So I changed it by a tiny, tiny, tiny amount, and I still got a very different solution. So this is the reason why you should care about chaotic solutions, is exactly this fact here, about them being super sensitive to initial conditions. Why does that matter? Well, when you try to throw something in a computer to have it solve it for you, it's going to make numerical rounding errors. That's just what computers do. They can't do infinite precision. They're going to round at some point. So if your ODE is chaotic, like that one, and you try to throw a problem at it for the computer to solve, you don't know if you're going to get the right answer, because if you're off by a little bit on initial conditions, you're off by a mile down the road. So this means you have to be wary when throwing things at a computer, because any rounding error the computer does is going to be really, really awful for predicting what's going to happen for the system. Now, in general, ODEs you see and you're going to want to solve aren't going to be chaotic, but these things do happen. They do appear, and the issue is if you try to solve them numerically, you're not going to get the right answer because you're going to be off by a little bit, which is going to cause you to be off by a mile down the road. So you really have to have a different way of solving these problems other than throwing them at a computer, because the computer can't do the right thing for you. So that's something just to keep in mind, just to know that it's there. It's a thing that exists when you just say throw everything at a computer and have it solve it. There are ODEs, difference equations. There are also ODEs that will do it too, where being off in the terms of a rounding error from a computer, no matter how much precision you have, is enough to throw off your answer. All right, so that's just something to keep thinking about for this section. That's all I really want to say for this video and about this section. The stuff is really cool, but it's a little hard to actually work out without a computer to do it. So I showed you some of the Maple stuff to work that out. But that's all I want to say for this video. Thanks a lot for watching, and then in the next one we'll move on to other stuff in Chapter 3 is actually next. So we'll move on to stuff in Chapter 3 with the next set of videos. Thanks for watching, and I'll see you in class.